Good evening, I am Shaiju, I am from chemistry department. So, today I will be talking about some basic concepts of stereochemistry. So, stereochemistry means it is the branch of chemistry that deals with three-dimensional properties of the molecules. So, before going into the main topic, we should have some idea about isomerism and isomers. What are isomers? So, isomers are compounds with same molecular formula, but it will have different structural or spatial arrangement. Okay. So, mainly the isomerism can be classified into two. First one is structural isomerism and the second one is stereoisomerism. So, the structural isomerism arises due to the difference in the structural formula, whereas the stereoisomerism arises due to the difference in the spatial arrangement. Again, if you see the structural isomerism, again it can be classified into chain isomerism, positional isomerism, functional group isomerism. Similarly, the stereoisomerism, again it can be classified into geometrical isomerism and optical isomerism. So, there is a strong correlation between the optical isomerism and stereochemistry. So, now we will see what is optical activity. It is the ability of a molecule to rotate the plane polarized light. If a molecule has the ability to rotate the plane polarized light, then that particular molecule is known to be optically active. Okay. Now, on the other hand, if the molecule does not have the ability to rotate the plane polarized light, then it is optically inactive. If a molecule rotates the plane polarized light towards clockwise direction or right, then it is termed as dextrorotatory. We will represent it with a small d or a plus sign. And if the molecule rotates the light towards the anti-clockwise direction, then we will term it as levorotatory and we will represent it with small l or minus sign. So, optical isomerism arises due to the difference in the effect of rotation of plane polarized light. Okay. Now, the optical activity has a strong correlation with the symmetry of the elements. So, we should have some idea about the different types of elements of symmetry. Here I have listed the different types of elements of symmetry: identity, proper axis of symmetry, plane of symmetry, improper axis of symmetry, okay, and center of symmetry. We will see first one, plane of symmetry. It is an imaginary plane which cuts the molecule, which bisects the molecule into two equal halves. Then that particular molecule is said to have plane of symmetry. Okay. Some examples I have shown over here. For example, if you see 2-chloropropane, I have shown a plane which cuts the molecule into two equal halves. When there is a plane of symmetry, that molecule is said to be achiral in nature. So, similarly, in the case of mesotartaric acid, there also we can find a plane which cuts the molecule into two equal halves. So, mesotartaric acid is also achiral in nature. Whereas, if you take 2-chlorobenzene or lactic acid, we cannot find such a plane which cuts the molecule into two equal halves. Therefore, these two molecules, the 2-chlorobutane and the lactic acid, are said to be chiral in nature. Next element of symmetry is center of symmetry or inversion center. It is a point from which lines are drawn in opposite direction. If these lines which are drawn in opposite direction meets the same or similar molecules or similar points, then we will say that this particular molecule is having center of symmetry. Some examples I have shown over there. Okay. Now, next one is axis of symmetry. It is an imaginary line passing through the center of mass of the molecule, about which the molecule is rotated by an angle 360 by n. If we get identical structures or indistinguishable structures, then that particular molecule is said to have axis of symmetry. For example, I have shown the examples of ammonia and water there. So, in the case of ammonia, that axis is denoted as C3. That I will explain. Okay. When ammonia is rotated about that particular axis by an angle 120 degrees, then we will get indistinguishable structure. So, 360 by 120 is equal to 3. That is why that particular axis is termed as C3 axis. Whereas, in the case of water, if you rotate it by 180 degrees about that particular axis, then we will get similar structures or indistinguishable structures. So, 360 by 180 is equal to 2. So, that particular axis is termed as C2 axis. Okay. Now, next is alternate axis of symmetry or improper axis of symmetry. Here, similar to the axis of symmetry, we will rotate the molecule about an axis by 360 by n. Then, it is followed by reflection by a plane which is perpendicular to the axis about which we have rotated the molecule. So, after the reflection, if you get similar structure or indistinguishable structure, then that particular axis is termed as improper axis of symmetry. So, improper axis means rotation followed by reflection. You will get identical structures. Okay. So, the fifth element of symmetry is identity. Identity means doing nothing to the molecule, means the molecule itself. Okay. Now, we will move to the next slide. Concept of chirality. So, what is a chiral structure? What is chiral structure? A chiral structure means an object or molecule is said to be a chiral if it has a plane of symmetry and the object and mirror images are superimposable. Whereas, chiral structure means the object or molecule which has no plane of symmetry and the object and mirror images are not superimposable. So, here I have given some examples. For example, if you take the letter P, the mirror image is not superimposable. If you take the letter A, the mirror image is superimposable. So, the letter P is said to be chiral and letter A is said to be achiral. Okay. Now, we will come to the chirality in organic molecules. If the carbon atom is attached to 4 different groups, then that particular carbon is known to be chiral carbon or stereogenic carbon or stereogenic center. So, here I have shown some examples of molecules with one stereogenic center and more than one stereogenic center. So, the stereogenic center is denoted by an asterisk star, you can see here. Now, what are enantiomers? Enantiomers are stereoisomers of a compound which are non-superimposable. Okay, means they are mirror images which are not superimposable. They can rotate the plane polarized light in opposite directions to an equal extent. For example, if you take plus lactic acid and minus lactic acid. Okay. Plus lactic acid, the specific rotation is plus 3.82 degrees, whereas for minus lactic acid, the specific rotation is minus 3.82. Okay. Now, we will see the representation of enantiomers. There are 3 different ways. First one is Newman projection formula. So, the Newman projection formula it visualizes the conformation of a chemical bond from front to back. For example, I have given an example of ethane here. So, in ethane there are two carbons. So, the front carbon is represented by a dot and the back carbon is represented with a circle. So, each carbon has 3 hydrogen attachments. Okay. Now, in the dash wedge line structure, as the name indicates, the bonds are represented with dash symbol and wedge lines and normal line. So, the normal line represents the bonds in the plane of the paper, whereas the wedge line, the thick line, represents the bond which are pointing towards the observer, and the dash line represent the bond which are pointing away from the observer. Okay. Now, the third way to represent the enantiomer is a Fischer projection formula. So, in the Fischer projection formula, it is a simple way to represent molecules. Okay. In the Fischer projection formula, we will use horizontal and vertical lines, mutually perpendicular horizontal and vertical line. Okay. The point of intersection of the two lines represents the chiral center or stereogenic center. So, this is the simple way to represent an edge viewed structure. So, by this convention, the bonds which are projecting towards the observer, that means represented by the wedge line, is represented at the edges of the horizontal line, and the bonds which are pointing away from the observer, means represented by the dashed lines, those groups are attached to the edges of the vertical line. Okay. So, I have shown some examples here. Now, we can represent the same molecule with different Fischer projection formula. So, how we can do that? There are some ways to do that. The first one is rotation by 180 degrees in the plane of the paper. Okay. So, I have shown some example here. If you see the first structure, okay, the vertical line H and OH, that when we are rotating by 180 degrees Celsius, the H will come in the place of OH and OH will come in the place of H. Similarly, if you rotate the vertical line, the CHO will come in the place of CH2OH and CH2 will go to the place of CHO. Okay. So, here the structures 1 and 2 are identical structures. So, the next method is keep one group fixed and rotate the other 3 groups in clockwise or anti-clockwise direction. For example, here I have fixed CHO group and rotated the other 3 groups. So, H will come in the place of CH2OH, OH will go to the place of OH and OH will go to the place of H. So, the structures 3 and 4 are identical. Now, the third method is double exchange, means 2 times we will do the exchange. For example, the fifth structure, here I have exchanged CHO and H. So, we will get the sixth structure, and here I have exchanged H and OH. So, we will get the seventh structure. So, here the structure 5 and structure number 7 are identical. Okay. This we will use while giving the configuration. Okay. Now, we have learned about enantiomers. Now, what are diastereomers? They are also non-superimposable stereoisomers, okay, but there is no mirror relation as in the case of enantiomers. For example, here you can see the first structure, okay, the mirror image of the first structure is the second one. Similarly, the third structure, its mirror image, the fourth one. So, the 1 and 2, the first and second structures are enantiomers because they are not superimposable mirror images. And similarly, 3 and 4 are also non-superimposable mirror images. So, they are also enantiomers. But if we take the structure number 1 and 3, they are also not superimposable, but there is no mirror relation. So, structure number 1 and 3 are called diastereomers. Similarly, structure number 1 and 4, there is also no mirror relation, but they are also not superimposable. So, they are also diastereomers. So, I have listed the main differences between enantiomers and diastereomers. So, enantiomers have same physical properties, whereas diastereomers, they have different physical properties. Enantiomers rotate the plane polarized light to an equal extent, whereas diastereomers, they also rotate the plane polarized light, but not to an equal extent. Okay. So, I have given some more differences. Next, we will talk about configuration, relative configuration. So, what is meant by configuration? Configuration means it is a specification of 4 different groups around the chiral carbon. Okay. Relative configuration means, as the name indicates, the configuration is related with something. Okay. The configuration of a particular molecule is identified by comparing it with some molecule of non-configuration. Okay. That is relative configuration. In carbohydrate chemistry, the configuration is assigned with respect to the configuration of glyceraldehyde. So, the glyceraldehyde, the Fischer projection formula of glyceraldehyde I have shown here. Here, the oxidized group is at the top. Okay. So, in that way we have to write the Fischer projection formula. I will explain the rules later. Now, in this Fischer projection formula, if the OH group is on the right side, then it is termed as D-glyceraldehyde. D means with capital letter D. The small letter D means dextro, that is different. So, here it is represented with capital D. If the OH group is on the left side of the horizontal line, then we will term it as L-glyceraldehyde. Okay. So, as I mentioned, the other stereoisomers are assigned by comparing it with the configuration of the D and L glyceraldehyde. Okay. There are some rules to be followed. As I said, while writing the Fischer projection formula, the most oxidized carbon attached to the chiral center is placed on the top of the vertical line, and the group with the carbon atom forming a part of the chain is placed at the bottom of the vertical line. The remaining groups are attached along the edges of the horizontal line. Okay. So, here you can see this is the Fischer projection formula of lactic acid. Here the OH group is on the left side. So, it is L-lactic acid, plus sign means it is dextrorotatory. Okay, that is different. Now, here the OH group is on the right side. So, it is D-lactic acid. Okay. Now, coming to absolute configuration, we have learned about relative configuration relating with something. This is the actual orientation of the 4 groups attached to the chiral carbon. Okay. So, while assigning the absolute configuration, certain rules are there that needs to be followed, which was proposed by Can, Ingold and Prolog, known as CIP system. Okay. Means we should prioritize the groups which are attached to the chiral carbon atom based on something. So, the first criteria is based on the atomic number of the atom which is bonded directly to the chiral carbon. Higher atomic number should give the higher priority. Okay. The second rule is, if the atomic number is same, then we should consider the mass number. For example, in the case of hydrogen, the isotopes of hydrogen. So, the one with highest atomic mass should give the priority. Next, if we can't decide the priority on the basis of atom that is directly attached to the chiral carbon, then we should go to the next atom. There we should apply all these rules, whatever I said. There also, if you can't find or you can't assess the priority, then you should go to the next carbon atom. So, it should be continued until we get the first difference. Okay. Maybe when we are working out some examples, you will get more idea. And if the molecule is represented using dash wedge line structure, then there is one rule that has to be followed. The lowest priority group, okay, the lowest priority group should be pointing away from the eye of the observer. If it is not, we have to somehow arrange the molecule in such a way that the lowest priority group is pointing away from the observer. Then you can find the configuration. But if you write the molecule in the Fischer projection formula, it is very easy, like comparatively it is easy to identify the configuration. Okay. But there are also some rules that has to be followed. We know that Fischer projection formula, we will write like we will represent the molecule by writing horizontal and vertical lines. Okay. The lowest priority group, okay, that has to be kept always in the top or bottom position. If it is not, if the lowest priority group is not in the vertical or horizontal, top or bottom, we have to bring that molecule to top position or bottom position by doing the double exchange. Double exchange I have already explained. Okay. Now, once you bring the lowest priority group to top or bottom of the vertical line, then you should give the number according to the priority 1, 2, 3 like that. Then you should count it 1, 2, 3. If your eye rotates in the clockwise direction while counting 1, 2, 3, if your eye rotates in the clockwise direction, then the configuration is termed as R. R means rectus, it is a Latin word meaning right. If your eye is going in the counterclockwise direction or left, then it is termed as S. S means sinister, meaning left. So, I have shown one example here, D-glyceraldehyde. If you take D-glyceraldehyde, first we have to give the priorities to the group. So, we will see what are the atoms which are directly attached to the chiral carbon. Here it is oxygen, in this case it is carbon, here also it is carbon, in this case it is hydrogen. So, comparing all these 4 atoms, oxygen should be given the first priority because it is having the highest atomic number. The second priority should be given to carbon, but here are 2 groups with carbon atom directly attached to the stereocenter. Then according to the rule we should see the next atom. So, here in the case of CHO it is C double bond OH. Double bond O means we can consider 2 times, oxygen we can consider 2 times. Okay. So, in this case it is 2 hydrogen and 1 O, but here it is 2 oxygen. So, definitely the priority should go to CHO, the second priority, and third priority it will go to CH2OH, and hydrogen is having the 4th priority. So, it is in the horizontal line. So, as I mentioned, it should be in the vertical line. Okay. So, we can do the double exchange. So, after doing the double exchange means first we will exchange, here I have exchanged H and CH2OH first, and second I have exchanged CHO and OH. So, the structure, this structure and this structure will be identical. So, we can find out the configuration. Now, the 4th priority group, the lowest priority group is in the vertical position at the bottom. So, now we can count 1, 2, 3. So, the rotation of eye is going in the right direction. So, it is denoted as R. So, in this case, in the case of L-glyceraldehyde, when you count, so the groups are same. Okay. So, first priority will go to OH, second priority CHO, third priority CH2OH, and 4th priority hydrogen. So, hydrogen again it is in the horizontal position. So, we will bring it to the vertical position by doing the double exchange. So, after that when you count 1, 2, 3, the rotation of eye is in the left direction. So, it is denoted as S. Okay. So, maybe today I will stop at this point. Thank you.